as you can see, there are certain circumstances in which aircraft electrical systems do come in very handy. And as you might guess, as an airframe mechanic, the FAA does want you to know about aircraft electrical systems, so therefore they will ask you a few questions on the airframe written exam about aircraft electrical systems. Let's lead off by talking about wire sizes. In the United States, the American wire gauge system is used to designate electrical wire sizes, and the number assigned to a size is related to its cross-sectional area. Now, the smaller the wire, the bigger the number, and vice versa. And you can see that by looking at this gauge right here. So the smaller the wire diameters, the larger the gauge numbers, and that's one of the things you need to know about this. Now, if you find an aircraft with aluminum wire in it, you should know that copper wire can be substituted for aluminum wire. Not only can it be, I think it's a darn good idea too. Not only that, if you do substitute copper wire for aluminum wire, you can decrease the size by 2 sizes. And as you well know, that means you go up in gauge number. When you decrease the wire size, the gauge number goes up. Now, if you do have aluminum wire in an aircraft, you should check it to make sure that nothing's smaller than number 6, because aluminum wire smaller than number 6 cannot be used in an aircraft application. Now, let's take a look at a question they're going to ask you about this on the test. They're going to say, what copper electrical cable size should be used to replace a number 6 aluminum electrical cable? Now, if you remember, you get to go 2 sizes smaller. That means you go up in gauge 2 sizes. So what gauge would it be? You've got it. It's copper number 8. So you've got it figured out. You can replace aluminum with copper, and you get to go up 2 gauge sizes when you do it. Now let's take a look at the primary considerations when you're selecting electric cable size. So you want to pick a wire cable and pick a certain size. What are the considerations? Well, let's take a look at them. First of all, the current carrying capability of the conductor. Can it carry the current? Next, the type of load. Is it continuous or intermittent? Next, allowable power loss. And finally, permissible voltage drop. So these are the primary considerations when you're selecting electric cable size. Now let's take a look at a question they're going to ask us about this. They're going to say, what is the allowable voltage drop for a number 18 copper wire that's 50 feet long, and it's to carry 12.5 amperes of continuous operation? You think, oh my goodness, how am I going to answer that? Well, here's what they give you. In the question, they give you the formula. And VD stands for voltage drop. And they give you resistance per foot for that particular wire. And in this particular case, it's 0.00644. They give you the length of the wire and they give you the amperes. And here's the formula. Voltage drop is the resistance times the length times the amperes. So now all you have to do is plug in the numbers with your electronic calculator, and you and I have solved the problem. So let's take a look at it. First of all, the resistance is 0.00644, and the distance is 50 feet, and the amperes is 12.5 amps. You multiply all that together, and your voltage drop is 4 volts. And that's all there is to it. And they will give you, believe it or not, all of this information on the test. Now let's take a look at a few things the FAA wants you to know about electrical wiring installation. First of all, you need to know that aluminum wire must be stripped very carefully when it's being stripped, because individual strands can become nicked, and after being nicked, they can break very easily. So be careful stripping aluminum wire. Now, 2 ways you can make installations are with open wiring, or you can put wiring in conduit. Well, open wiring, that's wiring not in conduit, has some advantages. Let you and I take a look at the advantages the FAA wants you to know about for open wiring. First of all, ease of installation. You don't have to mess around with a conduit. That makes sense. Simple maintenance. You can get to it easily, and reduced weight. You don't have the weight of the conduit. So those are the advantages of open wiring. Now you can bundle open wiring together, obviously, as is done here. But the bundle should be limited as to the number of cables the FAA wants you to know, and the reason for that is to minimize damage from a single electrical fault. What they're saying is you can get a short here, and if the wire gets very hot, you can run every wire in the entire bundle. So you need to think about that and limit the number of cables that you put in a bundle.
Now, when you're installing wiring in an aircraft, sometimes due to limited spaces, you don't have a lot of options. And sometimes you have to install electrical wiring somewhere near a line that holds flammable fluid. Now, if you're going to do that, where do you want the electrical wiring in regard to the fluid lines? And the answer is fluid, if it's going to drip, is going to drip down. And fire, if you have it, is going to send convective currents going up. So your choice would be to run the wires above the flammable fluid lines. And of course, you always want to secure those wires to the structure. So if you do have to install aircraft wiring near flammable fluid lines, locate the bundle above the flammable fluid lines. And of course, always securely clamp the wires to the structure.
Now let's assume you have a wire installed in an aircraft and that wire has a break in it. Can you splice it, or do you have to replace the entire wire? Well, as a general rule, splicing a wire is not a good idea. You would never want to splice a coax cable or an ignition lead or a thermocouple, or never would you want to splice in a place where you might have high vibration. And if you do splice wires, you should keep the splicing down to a minimum. But when it's approved, splices may be used. Now, only one splice is allowed between any two connectors, so you can't get carried away and put several splices in the wire. And when you have several splices located in one wire bundle like this, the splices should be staggered along the length of the bundle. Now, given all of that, occasionally you can put some splices in wires. Now, let's talk about the minimum radius of a bend in a wire bundle. Now, they're going to kind of confuse you just a little bit on the test, and they're going to refer to a minimum bend radii. That means more than one radius. There's two of them. That's all they're doing right there, or at least more than one anyway. So the minimum bend radii should be 10 times the outside diameter of the bundle. Figure out the outside diameter of the bundle and multiply by 10, and that is the minimum bend radii. Now let's take a look at passing cables through holes in bulkheads. Well, there's several ways you could do it. One way you could do it is put a connector right where you pass the cable through a hole in a bulkhead. But the FAA wants you to know on the test that if you put an electrical cable through a hole in a bulkhead, formers, ribs, firewalls, the wires should be protected from chafing by using a rubber grommet. So the FAA says the way to put a wire through this bulkhead or something of that sort on the test, now we're talking about, they say use a rubber grommet. All right, now let's take a look at coaxial cable. Coaxial cable, as you know, is a special type of cable. It has an insulation around the outside and a wire on the inside. Here's a coaxial cable right here. It's bent a little bit here, but that's coaxial cable, the black one. And the FAA wants you to know when installing coaxial cable, it should be secured along the entire length at 2-foot intervals. And also when you're routing it, route it directly as possible because you cannot bend coaxial cable as readily as others. So make sure that you route it directly as possible. And let's take a look at the last rule about coaxial cable, and that is it should be secured at 2-foot intervals. So you secure it as you go along at 2-foot intervals. Don't bend it much, make it a direct route, and secure it. That's what they want you to know about coaxial cable. Now, we talked about open wiring versus wiring in conduit. There's all kinds of conduits. People tend to think of metal conduits. You can also have plastic conduits. Here's a conduit right here. If a wire is installed so that it comes in contact with some moving parts, the FAA wants you to know, you should pass the wire through a conduit for mechanical protection. So mechanical protection is one of the reasons you have a conduit. Now, if you have several long lengths of electrical cable and they're being installed in a rigid conduit, how are you going to do it? And the answer is to dust the cable with powdered soapstone to reduce the possibility of damage to the cable as it's pulled through the conduit. Powdered soapstone is basically a lubricant for electrical cables. Let's talk about putting electrical terminals on the end of a wire like this. And this is an example of an electric wire terminal. In addition to providing good current carrying capabilities, these terminals must be designed to prevent circuit failure due to disconnection, due to coming apart. So you got to have them designed so they don't come apart and disconnect the circuit. So very often what has happened, instead of a hook type or a slotted type, they use a ring type of terminal like this. Now, when you're attaching a terminal like this to the end of an electric cable or a wire, the strength of this joint here, the cable to terminal joint, must be at least equal to the tensile strength of the cable or wire itself, because you don't want the joint to fail. If anything's going to fail, you want it to be the cable or the wire. Now, how do you attach terminals? Well, the accepted method of attaching these terminals to the wire these days in aviation applications is crimping them. So you crimp them to the wire, and that's an acceptable method of attaching a terminal to a wire in most aircraft general applications. Now, let's assume you're inspecting the terminal strips of an aircraft electrical system. What you need to determine is that the terminal studs are anchored against rotation. You don't want these studs rotating. So make sure that they're anchored against rotation. Now let's take a look at connectors. And one type of connector is what is known as an AN or MS electrical connector. And these are specifically designed to meet military specifications. By the way, AN is the abbreviation for Army Navy or Air Force Navy, and it's been superseded by MS, which stands for military specifications. So these are connectors that are specifically designed to meet military specifications. Now, there is both a pin and a socket section on connectors. The pin section of an AN-MS connector is normally installed so that these pins are on the ground side of the circuit, and this reduces the possibility of a short circuit by something hitting these pins. If they're ground side, that way you're not likely to get a short circuit. So make sure the pins are on the ground side of the circuit. Now, there used to be ways of attaching things to a pin or socket, like soldering and so on, that were acceptable, but a newer method of attaching a pin or a socket on a connector to an individual wire is by crimping. So you crimp them just like you do terminals. Now, it's necessary sometimes to use, if it is necessary, to use an electrical connector where it may be exposed to moisture. If you expect to have a lot of moisture, you need to have a special type of connector that provides some maybe plastic and rubber insulation. So if it's necessary to use an electrical connector where it may be exposed to moisture, use a special moisture-proof type of connector. Let's you and I take a look at grounding and bonding. What is grounding? Well, grounding is electrically connecting a conductive object to the primary structure, like the airplane's frame somehow, in order to prevent development of radio frequency potential. It's grounding it to the primary structure of the aircraft to prevent development of radio frequency potential. Now, aircraft components are bonded, as opposed to being grounded, bonded to allow electrical charges to move through the aircraft structure without causing sparks. And so if you want to allow electrical charges to move from one place to another in the airplane, for instance, an aileron could be bonded, you would use bonding to do that. Now, radio equipment is bonded to the aircraft in order to provide low impedance ground and to minimize radio interference. The way you'll do that is use a bonded cable. The cable itself has a shielding here that provides a bond. Bonding connections, by the way, according to the FAA, should be tested for resistance value. Measure the resistance value to make sure that there's not much resistance and it's doing its job properly. Now, when you're selecting hardware for attaching bonding connections to an aircraft structure, here's what you should take into consideration. When you're looking at the hardware for bonding, consider the mechanical strength, the ease of installation, and the amount of current to be carried. These are FAA test questions going by one right after the other. Let's take a look at copper jumpers. And by the way, this happens to be coming up here, a coated, nickel-coated or plated copper jumper, but this is a copper jumper. And here's a good case of using a jumper to bond a moving part. Copper jumpers are used to bond, and according to the FAA, here's an answer to a test question, non-continuous stainless steel aircraft components. Now, we couldn't find any stainless steel aircraft components, but anytime you have non-continuous components or moving parts, you can use jumpers to bond them together, and that's what we're talking about here. Now, they say when you're attaching bonding jumpers like so, avoid the use of solder. Don't solder them on. In this particular case, they've been screwed on, so avoid the use of solder. Let's take a look at electrical junction boxes and what the FAA wants you to know about them. Now, aircraft electrical junction boxes located in a fire zone are usually constructed of stainless steel. Once again, we couldn't find a stainless steel junction box, but they want you to know if it's in a fire zone, it usually would be constructed of stainless steel. I knew there was a word there somewhere. Now, it's important to prevent oil canning of electrical junction boxes to prevent internal short circuits. In other words, don't let this thing move around to the point where you could short something out. So prevent oil canning of junction boxes to prevent internal short circuits.
Well, now let's talk about circuit protection devices. And there are really three kinds of circuit protection devices. There are fuses, circuit breakers, and current limiters. Well, let's talk first about fuses.
Fuses are designed to provide the job of protecting electrical circuits from overheating. So the purpose of a fuse is to protect electrical circuits from overheating. Now, you can rate fuses by capacity, and the capacity of fuses is rated in amperes. So if you want to know how a fuse is rated, it's rated in amperes. Now, an important factor in selecting aircraft fuses is matching the capacity to the needs of the aircraft. So make sure you match the capacity of the fuse to the needs of the aircraft or the needs of the circuit. Now, the two most commonly used fused holders in aircraft circuits are the plug-in type, and here's a great example of a plug-in type, or clip types, and here's the clip type of fuse. Those are the two most common types, plug-in types and clip types. Let's you and I take a look at circuit breakers. Now, a circuit breaker is installed in an aircraft electrical system primarily to protect the circuit, and it should be located, according to the FAA, as close to the source as possible. Now, the advantage of a circuit breaker when compared to a fuse is the circuit breaker is resettable and reusable. You can use it time after time. You don't want to have them pop all that often, but they are resettable and reusable. That's the advantage of a circuit breaker. Now, the circuit breaker in the instrument lighting system, for instance, protects the wiring from too much current. That's the whole idea of a circuit breaker, is to protect the wiring from too much current. Now, an automatic reset circuit breaker should not be used in aircraft electrical systems as circuit protective devices because you want the pilot to be required of him some kind of action to reset the circuit breaker. You don't want it automatically being reset.
Now let's talk about current limiters. Now, a current limiter is essentially a slow blow fuse used in heavy power circuits, one with lots of amperage. They'll use a current limiter. Now, the advantage of a current limiter is that it will take an overload for a short period of time without blowing, and if you're the pilot, you would consider that a good thing. So you'll see current limiters generally in what I would call heavy-duty aircraft when they have heavy-duty amperage going right through that circuit.
All right, now let's take a look at switches. And what is the nominal rating of an electrical switch? Well, the nominal rating of an electrical switch is the continuous current rating with the contacts closed. That's what you can do continuously with the contacts closed. That's called the nominal rating of an electrical switch. Now, the nominal current rating of an electrical switch is normally stamped right on the switch housing. So you'll see it stamped right on the switch somewhere. Now, the good idea is the use of derated switches for known continuous load current applications, and that provides reasonable switch efficiency and service life. Just like derating an engine, you can derate a switch. Now, let's cover some terminology you need to know about aircraft switches. And the terminology goes like this. First of all, the poles tells you how many switches you have per control. For instance, if I'm switching two circuits at once, then it's a double pole switch. Here I have a landing light switch. If when I turned on the landing lights, I also had another circuit that I'm turning on with the same control, which would be, for instance, the taxi lights, two circuits on one control, then that's a double pole switch. If, on the other hand, the switch could go in two different directions, then it would be a double throw switch. The number of throws tells you how many directions that switch can go. For instance, if the switch goes on and turns on the landing lights, or could go down and turn on the taxi lights, then it's a double throw switch. Now, they're going to ask you some questions about this. They're going to say a switch which has an on position and an off position with no additional positions is referred to as what kind of switch? Well, it can only go in, you're only activating one circuit per lever, so it's a single pole switch, and it can only go in one direction, so it's a single throw switch. It's also called a two-position switch. What are those two positions? On and off. That's why it's called a two-position switch. Now let's assume that you had a switch you could install in a single wire circuit that required the switch to be manually held in the on position. If you release the switch, it goes to the open position. What kind of switch is that? Well, it's still single pole. You're only activating one switch per control, and it's single throw. It goes only in one direction. It's a two-position switch because it goes on and off, but it's what is known as a normally open switch. If you release it, it defaults to the open position, so it's called a normally open switch. If you have to hold it closed, then it's called a normally open switch. They say NO in that particular case. Now, let's assume you have a switch that's described as a single pole double throw switch. What does that mean? Well, that means you can go either direction with it. You could go one direction and turn on the landing lights, another direction and turn on, for instance, the taxi lights. Then this would be a single pole double throw switch, and the throw tells you the number of circuits that each pole can complete. One lever can go this way and complete a circuit, or go this way and complete a circuit. Then that becomes a single pole double throw switch. Nothing to it. Now, the FAA understands pilots pretty well. So to prevent inadvertent operation of a switch, that means accidental operation of a switch, the FAA says in some cases you should mount a suitable guard over the switch, knowing that sometimes you're going to have accidental operation of the switch, and when that would be a particularly disastrous thing, you put a guard over it. All right, let's take a look at a relay. They're going to ask you on the test, what is a relay? We'll talk more about this later on. But a relay is a magnetically operated switch. An electromagnet actually operates the switch. We'll talk more about that quite a bit later on. Let's take a look at a micro switch. Now, a micro switch is used primarily as a limit switch, normally in a gear operation, to control electrical units automatically. Normally, a landing gear would use a micro switch. It's the up lock or down lock switch in a landing gear operation. So micro switches are used primarily as limit switches to control electrical units automatically. Let's take a look at a rheostat. The FAA says if you're adding a rheostat to a light circuit to control the light intensity, and here's a good example of a rheostat, it should be connected in series with the light. That means not parallel to it, in series with the light. Now let's take a look at measuring instruments. The most accurate type of frequency measuring instrument is an integrated circuit chip having a clock circuit. So if you're trying to measure frequency, you'd use an integrated circuit chip having a clock circuit. Now let's take a look at an ammeter and the things you need to know about an ammeter. An ammeter in a battery charging system indicates the rate of current used to charge the battery. So what does an ammeter indicate? The rate of current used to charge the battery. Now, in installations where the ammeter is in the generator or alternator lead and the regulator system does not limit the maximum current that can be delivered, you put a red line on the ammeter at 100% of the generator or alternator rating. So if the regulator was not going to limit the maximum amount of current, you put a red line at 100% of the generator or alternating current. Now, a thermocouple type ammeter is something they're going to ask you about. A thermocouple type ammeter measures radio frequency alternating current, and the way it does it is the current heats the wire, and then the wire temperature tells current. They use that for alternating radio frequency current. All right, now let's take a look at a voltmeter. A voltmeter should be connected in parallel with the load. In other words, you can go right around the load and put the voltmeter on each side of it, and that's the proper way of connecting a voltmeter. Now, if you get the terminals backwards, if the plus terminal of the voltmeter is connected to the minus terminal of the source voltage and the minus terminal of the meter is connected to the plus terminal of the source voltage, they're going to ask you what's going to happen. And the answer is the voltmeter will read backwards. It reads the wrong direction. Hook it up backwards, it's going to read backwards. Let's take a look at an ohm meter. It's a good practice, by the way, to select an ohm meter range when you're selecting an ohm meter range in which readings are not too far from the mid-scale. You're really looking for mid-scale readings. Now, if you're troubleshooting an electrical circuit and you're using an ohm meter and it's properly conducted or connected across that circuit component, and some value of resistance is read. If you do get a value of resistance, that means the component has continuity and is not open. In other words, resistance means continuity, and it means that the circuit is not open. You're using it as a continuity checker in that particular case, and the fact that you get continuity means you don't have an open circuit. Now, when you're using an ohm meter to check the continuity of, for instance, a generator field coil, the coil, now we're talking about a generator field coil, should show very low resistance if it's a series field coil. We'll talk more about this later on, But the reason for that is the generator field coil, when it's in series, carries the entire output. So if you're using an ohm meter to check a field coil, it should show very low resistance if it's a series field coil. We'll talk more about that later on. We're talking about generator field coils. Now, an ohm meter can be used to determine the condition of an electrolytic capacitor. What happens is you first get very low resistance because the capacitor accepts the voltage, then high resistance. So if you use an ohm meter to check the condition of a capacitor, first you would have very low resistance, then high resistance. Now they're going to ask you on a test questions about a megometer. What in Sam Hill is a megometer? Well, it measures a lot of ohms, and it measures very high values of resistance, and that's what you need to know about that on the test. Here's an electromagnet. They're going to ask you some questions on the test about an electromagnet. It consists of an iron core or some kind of core, few turns of wire with a current running through it, and that sets up a huge magnetic field. Now, the strength of that magnetic field, they're going to call that the strength of the core on the test, but it's actually the strength of the magnetic field they're asking about. But the strength of the field depends on the type of material from which the core is constructed, the number of turns of wire in the coil, and the amount of current, or amperes, passing through this coil, and all of that determines the strength of the electromagnetic field. Now, one place where electromagnets are used in a sense is a transformer. Let's take a look at a transformer. Here's a transformer as it's installed in an aircraft. And of course, the purpose of a transformer is really to change the voltage of alternating current. So let's take a look at this schematic and see if we can figure out how this nifty transformer works. It's really pretty clever. First of all, you have an alternating current in this primary circuit, and it has loops of going around this core here. And that alternating current, of course, is changing its value all the time. And as the current changes in the primary, it creates an electromagnetic field in this core going around here. Now, this electromagnetic field happens to pass through another coil of wire in the secondary. It's a secondary circuit, and that secondary circuit has induced in it a current when the magnetic field changes in the core. So as this magnetic field changes in the core, it induces a current in the secondary. And here's the nifty part of it. The voltage in the secondary current is determined by the number of turns in the winding on the secondary versus the number of turns on the winding on the primary. For instance, if you want to triple the input voltage, what you have to do is have the primary coil have 1/3 as many turns as the secondary. Or to put it another way, the secondary should have 3 times as many turns as the primary. Now, let's assume that you have twice as many loops in the secondary as you do in the primary. If you have twice as many loops in the secondary as you do in the primary, the secondary then will have twice the voltage, so the voltage will be greater, but the amperage has to be less because you only have so much current. So when the voltage goes up, the amperage goes down. So the secondary will have an amperage that's less than the primary. Now, if a transformer winding has some of its turns shorted together, what's going to happen? Well, if these turns are shorted together, the transformer will get hot in normal operation. That's due to excessive current. So if you have turns of wire shorted together, the transformer will get hot. Now, the iron cores, we're talking about these iron cores right here, of most transformers are laminated. And the FAA will ask you why, and the answer is to reduce the effects of eddy currents. That's induced currents. You don't want any currents other than the ones you want, so they have a laminated core, and it helps to reduce the effects of eddy currents. Now let's take a look at some DC circuits. Now here's a good example of a DC circuit. We have a battery source here and several resistances going around, and the current remains constant all the way around here. If you have current in one spot, it's the same current in another spot all the way around. So in a DC circuit, the current remains constant. That's one of the things you want to know. Now, they're going to ask you, how do you determine resistance in a series circuit? Well, if you're using an ohm meter to do it, the way you determine resistance is to determine the voltage drop at each of the resistors. So you measure the voltage drop across each resistor, and that will give you, of course, the entire resistance, and that will tell you the voltage drop of each one gives you the entire resistance, and that gives you the resistance in the entire circuit. Now, when you're using the voltage drop method of checking resistance, the input voltage has to be maintained constant, because if it's not, you're not going to get a good value. So input voltage must be maintained at a constant value if you're checking the voltage drop across the resistance. Now let's take a look at some things you need to know about batteries. And one of the things you need to know is how you can connect batteries together. Now it is said there are 2 ways to connect batteries together. Actually, there are 3 ways you can connect batteries together. You can connect them in series, you can connect them in parallel, or you can connect them incorrectly. Let's take a look at it. First of all, in series goes like this. Here you have the minus end of a cell, here you have the positive end of the cell. You connect those together. Here you have the minus end and a positive end. And when you alternate them like this is connecting the batteries in series. It adds the voltage of the batteries up so you have more voltage, and that is an acceptable way to connect these batteries together. Now the other acceptable way of connecting batteries together is like this. You connect all the plus ends of the cells together, all the minus ends of the cells together, and that adds the voltage together. This is in parallel. It just acts as if it's one much bigger battery, and that's connecting these cells together in parallel, and that's a very acceptable way to connect the batteries. There's no problem there. Now, what do we have here in the middle? Well, we have 2 end batteries that are in parallel with a battery in the middle that's flipped, and that is an unacceptable way of connecting the batteries together, because there will be a short circuit from the center battery to the 2 end batteries, and that can be a very bad thing and cause a lot of heat. So the third way here is the unacceptable way of connecting cells or batteries together. Now let's take a look at NiCad batteries, or nickel-cadmium batteries, and here is a cell from a NiCad battery. And a NiCad battery has a lot of advantages. One of the things it can do is accept a charge very rapidly, and it can also deliver current very rapidly. However, if you have an excessive current draw, the NiCad battery can tend to heat up. And what happens is when the NiCad battery gets hot, the resistance, the internal resistance in that battery goes down. So if you have a current draw on the battery and it gets hot, the internal resistance goes down and the draw becomes even greater and it delivers even more current, gets hotter, resistance goes down, it delivers even more current, gets hotter, and that is what is known as thermal runaway, and you see an example of it right here, and that is called, once again, thermal runaway, and it comes from an excessive current draw on a NiCad battery, and that battery can get so hot that it will actually melt through the bottom of the aircraft and fall to the ground, and that is considered to be a very bad thing. So much for DC circuits. Let's you and I take a look at alternating circuits, or alternating current circuits as provided by, for instance, an alternator here. They're going to ask you in a test, what is the advantage of alternating current? Well, you can use a transformer to step it up to very high voltage, and then it can be transmitted with low power loss. So an advantage of AC is it can be transmitted at high voltage and low power loss. Now let's take a look at another advantage of using AC electrical power in an aircraft. And the advantage is you can use a transformer. And through a transformer using AC, voltage can easily be changed. It can be stepped up or stepped down. That's the real advantage of using AC current rather than DC current. Now, one of the problems you can have with AC current is kind of like trying to get a car that's stuck unstuck. You need everything pushing and pulling at the same time. And if you don't have this alternating current all in phase, with it all pushing and pulling at the same time, you can have what is known as power loss. Well, in an AC current with no phase, lead, or lag, real power equals apparent power. We'll talk more about that later on, but that is a test question, and it has to do with whether you have inductance in the circuit and so on. And all you need to know is if there's no phase, lead, or lag in AC current, then real power equals apparent power. You're getting all the power out of the circuit that it's capable of giving you. Now let's talk about another component of an aircraft, and that is called a capacitor, and this is a big capacitor. Now we talked about batteries earlier. Batteries store a charge. Well, capacitors also store a charge, and they can store tremendous voltages. They have electrical plates in them that can become charged. They have an insulation between the plates. They can become charged with very high voltage, have lots of power in them. In fact, they can be very, very dangerous when you're working on them. So when you're handling a high voltage capacitor in an electrical circuit like this one, be sure it is fully discharged before removing it from the circuit. You actually want to short it out, make sure it's discharged, because otherwise it could actually become very dangerous. Now, in addition to storing a charge, there's one other thing a capacitor will do that is really neat. It will pass AC current and stop DC current.
Well, where are you going to use that neat little trick? Right here with a generator. Let's assume the brushes on this generator are putting out a little bit of interference. Really, that's AC current the interference is. Well, you want the DC current to go to the battery, but you would like to drain off that AC current and maybe short it out to ground. So what you do is install a capacitor in parallel with the load of the generator and take it to ground. And what will happen is it will pass the AC interference and short it to ground, and it won't allow DC, so you don't lose any of your DC current. That all goes to load. So if you want to minimize radio interference, install a neat, tricky capacitor in parallel with the load on a generator.
Now, another electrical component we need to take a look at is a diode, and that's an electrical component that lets current flow only in one direction. You can check a diode, and with an ohm meter is a good way to do it, but you should follow a procedure. So let's take a look at that procedure. First of all, a diode is checked for an open or a short circuit. You should disconnect it from the circuit, and by the way, you should check it in each direction. So if you want to check it with your ohm meter, disconnect it from the circuit and check it in each direction. Now let's you and I take a look at motors and generators, and they're electrically and mechanically very similar to each other. They have all the same components, and they're just wired just a little bit different. We'll talk about that. First of all, let's take a look at how generators are rated. Well, generators are rated in amperes at rated voltage. How are generators rated? In amperes at rated voltage. Now, the generator rating will usually be found stamped on the generator somewhere. So look around the outside of the generator somewhere, and you'll usually find the generator rating. All right, let's take a look at the parts of both a DC motor and a generator, and the same parts apply in each case. You have an armature assembly, and this is for a DC motor, but it's the same as far as a generator is concerned. You have an armature assembly, you have a field assembly, a brush assembly, and an end frame. Now let's take a look at it and see if we can make some sense out of this. First of all, the way a generator works is you take a magnet and pass it by some wire, a coil of wire, and you'll induce a current in that coil of wire. Well, here's the way you can do this. First of all, let's assume that this is an electromagnet. We'll call it a field because it sets up a magnetic field. And so when you put a current in this coil of wire, you have an electromagnetic field around the outside of the generator or motor. You might have it in several places. Let's make this a generator to begin with. And then here you have an armature, which is a coil of wire that rotates around. And when you rotate this coil of wire past the electromagnet, it induces a current in that coil of wire, and it becomes a generator, or it could be an alternator. But it induces some kind of current in a coil of wire, and then it becomes a generator. Well, the rotating part is called a rotor, and if it's the part that gets the current induced in it, it's called the armature. It's a rotating armature. A stationary part is called a stator, and in most generators, the field is stationary. So the stator is the field right here, and that becomes a generator. So if you rotate a coil of wire around an electromagnet, you're going to induce a current in that coil of wire. If, on the other hand, you put a current in that coil of wire and then you have another electromagnet, you can see what's going to happen is you now have two magnets, and they'll repel each other or attract each other, and then it becomes a motor. So now you've got it all figured out right there. Now, the reason you have brushes is so you can have contacts on this rotating member, and these contacts will take away or give to the device the electrical energy. So the brushes are on a commutator, which is on a shaft. The commutator rotates around. The brushes make connection, and that's how you transfer the electrical energy out of the rotating parts. The end frame just simply holds those brushes and holds this whole thing in place right here like so. So that's all there is to it. All right, now let's take a look at some questions they're going to ask you about specific parts, and that's the armature assembly. Now, on most small motors and generators, the armature rotates, and here's an armature assembly like so. And they're going to say, why would you have a magnetic brake in an armature assembly? Well, a magnetic brake is used to stop the rotation of an electric motor, and the armature operates by use of a friction brake applied to a spring and released by a magnet. And all you're trying to do is stop the rotation of the motor. For instance, a landing light retraction motor would most likely have an armature brake in it. It's something to stop the motor so it doesn't keep on grinding away. When this landing light is retracted, you'd like for it to quit so it doesn't grind it into the aircraft itself. Now, the heart of any electric motor or generator is the armature, and there are a couple things that can go wrong with the armature. First of all, you could have shorts, or you could have opens in the windings. So you can test for that by using a device known as a growler. I want to point out right now, a growler is not a reference to my personality in any way at all. Maybe on some Monday mornings, yes, but not generally. I am not a growler. That's a device designed to test an armature. And what a growler is basically a coil with a V in it so that you can put the armature in that coil. It sits down in the coil with a V shape here, and you connect the growler to 110 volt AC, and when you do that, it makes a humming noise or a growling noise, and that's why it's called a growler. Very good, very good. You got it. Okay, now, here you have a circuit with alternating current in it. In fact, a coil with alternating current. And then you put another coil of wire, which is the armature, on top of it. What have you just created? You have created a transformer. You're inducing a current in the secondary winding, which is the armature. So there's now current flowing through here. And you can test to see if current is flowing where you want it to flow by using a 110 volt light with a couple probes on it. You put a probe on one segment and then put a probe on an adjacent segment. And if the windings do not have opens in them, then the light will light. Now, you don't want the segments to have opens in them. The windings should be continuous. So by checking adjacent segments, you can see if the light lights, and if it does, you know it's working properly. So how do you test for an open? Well, to test generator or motor armature windings for opens, place the armature in a growler. We've already figured that out. Connect the 110 volt test light on adjacent segments, and the light should light. And if it does not light, you have an open. Now, let's check something else while we're at this here. You could also use a growler to check for shorts. What you can do is put one probe on a segment and another probe on the center post, and you should not have any electrical connection there. And if the light does light up, that means you have a short. Now, as you might guess, the FAA will try and confuse you on the test. You can use a growler to test for opens, and you can use a growler to test for shorts, so they will try and confuse you between the procedures for doing that. To test for opens, you put the probes on consecutive segments, and the light should light. If it does not light, then you have an open. To test for shorts, you take a segment and the center post, and the light should not light. Now, if you've got that figured out, you've figured out the heart of a generator or a motor. Now, the field assembly we talked about earlier, and the field assembly is the part in most generators and also most motors that does not rotate, and it sets up the electromagnetic field that we're talking about. And the field assembly is very important. It's essential to the motor or generator. It's got to be there. Now, the only practical method of maintaining a constant voltage output from an aircraft generator under varying conditions of speed of load is to vary the strength of the magnetic field. So the regulator varies the strength of this magnetic field. So how do you maintain that? Do you do that to vary the strength of the magnetic field? And that's the way you change the output of the generator or keep it constant. Now, there's a concept you need to know about, and that is residual voltage. If this is an electromagnet, what happens is, this field is an electromagnet. If you take the current off the electromagnet, there will still be some magnetic attraction there because you've magnetized the field shoes. So residual voltage is the result of magnetism in the field shoes, and that means that if this were a generator and you spin the armature, even though the field is not energized as an electromagnet, you'll still get something out of the generator, some voltage out of it, because there's some magnetism that remains. It's called residual magnetism, and it gives you residual voltage. So that's where residual voltage comes from. All right, now, here's an example about this on the test. If the positive field lead between a generator and a generator control panel breaks, in other words, you have no generator field current, and it's shorted while the engine is running, a voltmeter connected to the generator output would indicate what kind of voltage, and the answer is even though you have no electricity in the field, you'll still get residual voltage. Now, the direction of rotation of a DC motor can be changed by reversing the electrical connections to either the field or the armature windings. So if you want to change the direction of an electric motor, just reverse the electrical connections to either the field or the armature windings. Some electric motors, by the way, have actually two sets of field windings wound in opposite directions, so the motor can be operated in either direction. Now, they'll ask you, what are the pole pieces or shoes used in a DC generator? And the answer is they're part of the field assembly. The field has shoes in it, and that's where the residual voltage is, or the residual magnetism is. So pole pieces or shoes, they're going to ask you, what are they as far as being used in a DC generator? And the answer is they're part of the field assembly, and that's what you need to know for the test. Now, the poles of a generator are generally laminated. You need to know that also to reduce eddy current losses. They're constructed in a laminated fashion, and that reduces eddy current losses, and that's another specific you need to know for the test. Now, what is a method used to restore generator field residual magnetism? In other words, some residual magnetism in this field is useful and valuable. So if you want to restore it, what do? The answer is you flash the field. You put an electric current through the field, and that restores residual magnetism. So you can flash the fields, and that's another question they're going to ask you on the test. Let's take a look at the brush assembly. The brushes, of course, as we mentioned earlier, are pressed against the commutator, and they transfer electricity. Now, in a generator, this brush arcing is being kept very low by springs. You have springs here. So what do you need to know about that? Generator brush arcing is low due to spring tension. Springs hold the brushes onto the commutator. There's another thing you need to know about a generator brush, and that is the brush pigtail, and there's the brush pigtail back in here, eliminates sparking to the brush guides. The pigtail transfers the electricity and eliminates sparking to the brush guides caused by the movement of the brushes within the holder. So the pigtail basically carries the electricity rather than the brush connecting to the holder. They're going to ask you also, what is the purpose of a commutator in a DC motor? Well, the commutator's on the shaft, and the purpose of the commutator is to reverse the current in the coil when the coil becomes parallel to the lines of force. That's a very fancy way of saying a commutator on a DC motor is wired so that you reverse the current so you constantly get DC. Because if you remember, a magnet has both positive or north and south poles, and otherwise you get AC current. So you've got to reverse the current to keep it from being AC, and it's the commutator that does that. And the magic words for the FAA written exam is the commutator reverses the current in the coil when the coil becomes parallel to the lines of force. They're also going to ask you on the commutator, what is the mica insulation between the commutator bars of a DC generator, and how much should they be undercut? And the answer is the mica insulation separates the two different circuits that you have to have inside the commutator, one for each direction of the electricity, and that mica insulation separates those, and they should be undercut equal to the width of the mica. In other words, when you overhaul a commutator, you should make sure that the mica insulation has been made grooved down to an undercut equal to the width of the mica. All right, now let's take a look at some motor designs. There are three basic types of DC motors, and these three types are, first of all, series wound, shunt wound, and compound wound, which means it's both series wound and shunt wound at the same time. Now let's take a look at what they're talking about when they're saying this, and we're talking about how a motor is designed and whether it's series wound or shunt wound. We're talking about how does the electricity flow through the motor to the armature. And if it's series wound, all of the electricity that goes through this motor goes first through the field and then to the armature. In other words, the field and armature are in series with each other, and that changes the characteristics of the motor. Now let's take a look at the characteristics of a series wound generator. First of all, it could either be a motor or a generator, by the way, that could be series wound, because remember, motors and generators are almost the same thing. So first of all, let's take a look at a thing you need to know about a DC type generator, series wound. And one of the things you know is it's not used as an airplane generator. Series wound DC type generators are not used as airplane generators. That's something you need to know for the test. Now let's take a look at something you need to know about a series wound motor, and that is the field windings. The windings in the field are, and by the way, they consist of a relatively few turns of heavy wire, are connected in series with the armature winding. Well, that is the purpose of a series wound motor. The field and the armature are in series with each other, and the field has relatively few turns of heavy wire in this particular case because all of the current going to the motor goes through the field. Now, the series wound DC motor will normally require more current at low RPM than at high RPM. That is one of the characteristics of a series wound DC motor, more current at low RPM than at high RPM. And the starting current of a series wound DC motor in passing through both field and armature windings, which is what series does, produces a relatively high starting torque, which is why that's generally used as a starter motor or a landing gear motor, because it has a very high starting torque, and that is a series wound motor. Of course, they're going to ask you specific questions about this on the test. They're going to say, all right, suppose you do want to raise and lower landing gear like so. What kind of motor would you use? Well, the electric motor used for raising, lowering the landing gear should be a split field series wound motor. So it is a series wound motor for landing gears. Now, another way generators and motors can be wound is shunt wound. Now, shunt wound is, instead of series, parallel. And what that means is the current flows in parallel between the armature and the fields. So a shunt wound DC generator, they're going to ask you in the test, is connected how? Well, it's connected by shunting both fields across the armature. Instead of being in series, it's parallel. That's called shunt wound. Now, the last winding design we need to talk about is compound wound, and it is compound. You can see it's complicated if nothing else. It's a combination series wound and shunt wound winding, and they're only going to ask you one question about this on the test, and it has to do with regulating the voltage output of a compound wound DC generator. They're going to say, how would you do that? Well, if a compound wound DC generator, the way you regulate the voltage output is to vary the current flowing through the shunt field coils, not the series field coils, but the shunt field coils, and that's the answer to that question right there. That's how you regulate the voltage on a compound wound generator, vary the current through the shunt field coils. Now let's take a look at another concept, and that is armature reaction. And here's an armature. We saw that before. Armature reaction is the shifting of the magnetic field, the field in the generator or motor, due to a field set up by the armature itself, and that's called armature reaction. Now, the effect of armature reaction is proportional to the load on the generator, and it's the amount of what they call neutral plane shift, and it's proportional to the load on the generator. Now, you can use methods to overcome the effect of armature reaction, and one of those methods is through the use of interpoles. You have poles in the field. Here's poles going around the field. Then you have little interpoles in between those poles, and they overcome the effect of armature reaction or the shifting of the field in the generator or the motor. Okay, now, so reducing field strength is not one of the purposes of an interpole. So they'll say, is reducing field strength a purpose of an interpole? And the answer is no, it is not. It's to shift the field back to correct for armature reaction. How about that? All right, let's take a look at how you regulate the voltage of a generator. Now, here is a schematic of a voltage regulator, and essentially what you do is you change the amount of current that goes through the field. And the way you change the amount of current that goes through the field is you change the resistance in the circuit for the field, and you can change the resistance in the circuit by field by inserting resistance or taking resistance away. In fact, what you have is a little vibrating device that alternately puts this resistor in or out of the circuit, and the more that the resistance is in the circuit, the lower the field voltage and the lower the output of the generator. And it vibrates back and forth, and on average it keeps the right voltage in the field and therefore gets the right output of the generator. So a voltage regulator controls generator output voltage by changing the resistance of the generator field circuit, which varies the current flow to the generator field coil. Now, if a generator is equipped with a vibrator type voltage regulator like this, the actual time the voltage regulator remains open depends on the load carried by the generator. And of course, the more load is, the more excited the field has to be and the less resistance there is. Now, if a short occurs between the positive armature lead and the field lead of a shunt generator, which has the voltage regulator located in the positive side of the field circuit, the voltage will increase. Now, why would that occur? Because it takes the resistance out of the circuit. So anytime you take the resistance out of the circuit, the voltage is going to increase. So one more time, let me just say it. So the generator voltage will increase under these conditions if a short occurs between the positive armature lead and the field lead of a shunt generator which has the voltage regulator located in the positive side of the field circuit. If you get a short, then the generator voltage will increase. All right, here's another question they're going to ask you, a little bit complicated. If the reverse current cutout relay contact fails to open after the generator output has dropped below battery potential, what will happen? And the answer is current will flow through the generator armature opposite the normal direction and through the shunt field in the normal direction. So let's talk about that one more time. You have a reverse current cutout relay. Contact fails to open after the generator output has dropped below the battery potential. Now what we're talking about here is, just to put this into English, you have a generator and a battery, and the generator is dropped below battery. Now what's going to happen is the battery will motorize the generator. We're translating this in English, and it means current will flow through the generator opposite the normal direction, and it still continues through the shunt field in the normal direction, and you've converted your generator into a motor. So what happens if the reverse current cutout relay contact fails to open? Then what's going to happen is you're going to motorize the generator. All right, here's another thing they're going to ask you. They're going to ask you about the over voltage control on a generator. It automatically protects the generator system, and the way it does it is by opening the shunt field circuit. Once again, you're opening the field, and therefore you're controlling the voltage of the generator. A twin-engine airplane like this, of course, will have two generators, and even if they're both DC generators, it's important that the generators be parallel to each other, and by that I mean the voltage should be about the same. If any one generator in a 24-volt DC system shows low voltage, then the most likely cause is an out-of-adjustment voltage regulator. So you can adjust the voltage regulator to make sure that they are about equal to each other. Now, when DC generators are operated in parallel to supply power for a single load, their controls include an equalizer circuit to assure that all generators share the load equally. So you do have an equalizer circuit. Now the equalizer circuit operates by increasing the output of the low generator and decreasing the output of the high generator until they're about equal. Now big airplanes like this Boeing 727 have, instead of DC generators, alternators, or alternating current generators they're called, but they produce alternating current. Now paralleling alternators or AC generators is an entirely different kind of thing. You have two things to take into consideration: voltage and frequency. Now the frequency of an alternator is dependent upon RPM. The faster it turns, the higher the frequency. Now when AC generators are to be operated parallel, then the frequency and voltage both must be equal. You got to keep both of them equal. In addition to AC generators, you can also have AC motors. Now there's two types of AC motors used in aircraft systems. They are the induction and synchronous motors. And this tachometer up here is a very good example of a synchronous motor. A tachometer actually operates with a synchronous motor. Now let's take a look at a question back to AC alternators they're going to ask you about on the test. They're going to say how many cycles of AC voltage are produced by a 6-pole alternator of the revolving field type for each revolution of the rotor. Okay, a 6-pole alternator has 3 north poles, 3 south poles. That's 3 pairs of poles, and so therefore you would have 3 cycles. It's pairs of poles that make a cycle, so you'd have 3 cycles of AC voltage produced by a 6-pole alternator of the revolving field type for each revolution of the rotor. Aren't you glad you found that out? All right, let's take a look at the voltage output of an alternator, how it can be regulated. And the answer is by controlling the voltage output of the DC exciter. That's another way of saying the field. So you regulate the voltage by regulating the field, or the DC exciter. Now, aircraft which operate only AC generators or alternators as a primary source of electrical power normally provide current suitable for battery charging. How? And the answer is through the use of a step-down transformer and rectifier. Why do you have a transformer and rectifier? Because you have to get the voltage from AC to DC and at the proper voltage level. So you have normally a transformer and a rectifier to charge the battery, because the battery is DC even though you're using AC current. Now here's something really elegant. It's a starter generator. We said they're very similar to each other, generators and motors. So you can see that you can have them both combined into one. That's what this is, a starter generator used in turbine-powered aircraft. They're going to ask you 2 questions about starter generators, and they both have to do with cooling them. They're going to ask, how do you cool a starter generator during ground operation? Well, during ground operation, they're cooled by an integral fan. There's a fan in here that provides cooling air to the starter generator. Now let's talk about the AC generators, alternating current current generators that are used on big airplanes like Boeing 727s, transport category aircraft. Now, we talked earlier about generators, and we said they have commutators so that they pull off DC current. But on these big alternating current generators used on 727s, you have alternating current. Instead of a commutator, they just have a slip ring. And what happens is, of course, the field goes by these windings and produces alternating current, and the frequency of that current depends on how fast this generator rotates. The faster it rotates, the faster the frequency will be. Well, if you have, we'll say, 3 alternating generators going at once, you want them all to be synchronized. In fact, you want them at the same frequency. So what you need to do is you have to have all of the alternating current generators, or alternators are called, but they call them generators when they're big aircraft, so they're alternating current generators on big aircraft. They all have to be rotating at the same constant speed, or else they'll be on different frequencies, and one's pushing, the other will be pulling. So you've got to have them all at the same speed. So therefore, you have to have what is known as a constant speed drive to keep all of the generators turning at the same speed. So a constant speed drive uses a governor-controlled variable delivery hydraulic pump and a hydraulic motor to maintain a constant output RPM. So the frequency will be the same, and so therefore you have a stable AC generator frequency, and that's very important. So a constant speed drive unit drives a generator through the use of a variable hydraulic pump and a hydraulic motor. It's almost like an automatic transmission driving the generator. And a constant speed drive driven generator is usually cooled by an oil spray, because these things get hot, so they have to be cooled by an oil spray. Now let's assume you are airborne, flying along in an airplane that has constant speed drives, and let's assume that you get some kind of malfunction, such as an over temperature. Well, the thing that you need to know is that a constant speed drive can be disconnected. You do it with a switch in the cockpit, but the thing you need to know is if they are disconnected, one of them becomes disconnected, you can only reconnect it on the ground. So constant speed drives can be disconnected in the air, but they can only be reconnected on the ground. Now let me ask you a question. Do you think a beautiful modern piece of equipment like this would employ a clunky system like a constant speed drive and a generator? Mais non. The French would never do something like that. They would use instead what you see right here, and that's an integrated drive generator. And what that does is it combines the constant speed drive and the generator into a single neat little package. Let's take a look at that package. You'll see how neat it is. Right here is the whole thing, very simple. It's an integrated drive generator, and it employs a high output AC generator and a brushless system to produce current very elegantly and very lightweight.
Now here's another look at that neat little package that an IDG is. And in here there's an oil filter, because there's a lot of turning and twisting going on in there, so it's a good idea to have an oil filter. You should check that oil filter every now and then and check it for contamination. Well, what if you find chunks or pieces of metal? Well, in that case, the IDG must be replaced if the scavenge oil filter is contaminated, and I'd consider chunks or pieces of metal contamination, so you'd have to replace the entire unit. Well, that's a great look at an IDG. Now let's talk about rectifiers.
A rectifier converts alternating current to direct current. They're going to ask you, what is the purpose of a rectifier? And the answer is to change alternating current to direct current. That's the purpose of a rectifier. So here we have an alternator. We're charging a battery with it. In order to do that, we have to have a rectifier. So an example of a question they're going to ask in a test, they say you have an aircraft that has no DC generators, only has AC alternators or generators. How do you keep the battery charged? And the answer is you use a rectifier. If all you have is an AC generator, no DC generator, you're going to have to use a rectifier. All right, to go the other direction, you need an inverter. Now, an inverter, and this is what an inverter looks like from the outside, is necessary to provide alternating current from DC or battery generator type systems when you have nothing but DC sources. Now, one type of inverter is called the inductor inverter, I should say. And the inductor inverter is basically a motor and an alternator that provides AC current when it gets done. It actually rotates around, has a rotor in it, and it's controlled by the DC stator field current. The current in the stator field for the DC portion of this thing controls the output for the AC output. And that's what you need to know. It's basically a combination of a motor and a generator. You have a motor turning a generator, and the output is AC current, and the output voltage is controlled by the DC stator field current. That's what you need to know about it. Now, the FAA wants you to know about electrical equipment adjustments and overhaul. Now, major adjustments on equipment such as regulators, contactors, and inverters are, according to the FAA, best accomplished outside the airplane on test benches with the necessary instruments and equipment using adjustments, procedures, and so on as outlined by the equipment manufacturer. And you cannot go wrong following the manufacturer's recommendations because the FAA must approve the manufacturer's recommendations. So here's another way of putting it. When overhauling electrical equipment, all necessary information should be obtained from maintenance instructions published by the aircraft and/or equipment manufacturer. They are the source of all knowledge for overhauling electrical equipment. All right, let's take a look at aircraft lighting systems. One of the things you need to know about is position lights. Well, aircraft operating at night must be equipped with position lights that meet the minimum requirements specified by the Federal Aviation Regulations. The Federal Aviation Administration establishes the minimum standards concerning the number, color, location, and intensity of position lights for navigation on civil aircraft. Now, the color and location of aircraft position lights on airplanes are, when you're looking forward, looking back at the front of the airplane, red is on the left side of the aircraft and green is on the right side of the aircraft. Aft of the aircraft, white light is to the rear. Now, if one switch is used to control all navigation lights on the aircraft, the lights are most likely connected in this fashion, parallel to each other and in series with the switch. And that's a question on the FAA written exam. Let's talk about anti-collision lights. Now, when you're installing an anti-collision light, install a switch independent of the position lights. You should not have them tied together. So during inspecting an anti-collision light installation for condition and proper operation, you should determine that the anti-collision light can be operated independently of the position lights, and that is important.
Now let's talk about landing lights. A landing light is an example of a circuit that's considered to be an intermittent duty circuit. In other words, it's not on all the time. So what is the maximum amount of time that a circuit can be in operation and still be considered to be an intermittent duty circuit? In other words, what's the maximum time expected of an intermittent load, such as a landing gear, flaps, trim motors, and landing lights? Well, they define an intermittent load as one that will be operated for 2 minutes or less. So an intermittent duty circuit is one that can be in operation up to 2 minutes. What they expect is that during heavy intermittent loads, such as operating a landing gear, that you will create a temporary overload. So they designed the electrical system to tolerate it for up to 2 minutes.
Now let's talk about what I think is the granddaddy of all the electrical system questions, and that is the one that they ask you about here on Figure 20. And what they ask you to do is to interpret a schematic, and this happens to be a schematic of a landing gear warning system. Now they're going to ask you on the test, what's the minimum circumstance that will cause the landing gear warning horn to indicate an unsafe condition? Well, if you think this through a little bit, the landing gear warning horn probably tells you when the landing gear is not down and locked, and you would like to have all 3 wheels down and locked, so we'll probably check if even just one of them probably will cause the horn to sound. So let's work our way through. And by the way, for any circuit to activate or to work in this situation, what you have to have is a continuous path from the voltage source to any ground. Here's a ground, here's a ground, here's a ground. And if you can get a continuous path from the voltage source to the ground, then that circuit will be in play. It'll be working. So let's take a look at it. First of all, these are the landing gear switches that tell you when the landing gear is down and locked. And when the landing gear is not down and locked, this switch is closed. Getting the gear down and locked opens the switch. So this gear is not down and locked. The landing gear switch is closed, and you see that you have a path all the way through to this relay, but then the path is interrupted at the relay because we need to activate that relay. Now, how can we activate that relay? Well, let's go up here to the voltage source, and here we go from the bus down this direction, and you can see that if you have either throttle retarded, then you have a continuous path through that relay to ground, and then of course we'll activate that relay and close this switch, and that will give you a path through the horn and through this warning light and through this flasher. By the way, that looks like a current limiter to me, but the FAA tells us right here on the drawing that that's a flasher, so that's a self-interrupting switch that will cause this light to flash, and that will take the current all the way back to the voltage source. So now we have a continuous path. You can see that with either throttle retarded, this relay is closed, and when that relay is closed, you have a continuous path from the 24-volt bus through the horn, all the way down through the landing gear switch to ground, and that assumes, of course, that this landing gear is not down and locked. So what we have just learned is that the horn will sound anytime you have any landing gear not down and locked and either throttle retarded. That was obviously too easy for everybody, so let's do another one. Let's take a look at what will illuminate the amber indicator light. Well, the amber indicator light is this light over here in the right corner, and it says A on it. That tells you it's amber. And what we have to do is get a continuous path from the voltage source, which is the bus, all the way along here, all the way to ground. And that occurs when these switches are closed, and these switches are closed when the landing gear is up and locked in the up position. Then all three switches are closed, and then you'll have the amber light telling you the gear is up and locked. So closing the nose, the left and the right wheel gear fully retract switches will then give you that amber light telling you that gear is up and locked. Well, that was easy, so let's you and I do another easy one. Let's take a look at figure 19. And in this particular case, let's assume that you're a mechanic, you're working on an airplane, you're doing a landing gear retraction test. You've got the aircraft on jacks, and the conditions you have now is one or more of the throttles are retarded, and the landing gear is in transit. That means it's in any position between retracted and down and locked. Now, what they're going to ask you is what's going to happen to the warning horn and what's going to happen to the red position light. Well, let's take a look at this drawing and see if we can figure it out. What we have to do is figure out a continuous path from the electrical source, which is on the left-hand side in this particular case, here's your bus, to the ground, and most of the grounds in this drawing are over here on the right-hand side. Now let's go to the lower right-hand corner and read this note, because this note is very, very important to us. It says, note the switches shown are on the gear down on the ground position. So we're assuming the gear is down, the aircraft is on the ground, and that's how these switches are shown right now. Now, we have a green light, by the way, and I'll tell you right off that this aircraft has a green light when everything is okay, and a red light when the gear is up and locked, and when the aircraft gear is in transit, neither one of these lights are lit. Now, they're asking us about the red light, so let's follow that through with the red light and see if that's the case. So we'll start over here in the lower right-hand corner with ground, and then we'll follow what happens with the red light. So here's lower right-hand corner with ground. We'll go through here, and one way you could make this red light is do a push to test, because there's a little switch right there, and then you'd send it right over there to the power source and the light would come on. The other way, of course, is you follow the normal path for the light, and that's not the push to test, that's this direction right over here following wire number 8. So let's you and I follow wire number 8 and get over here to the power source if we can. Following wire number 8, we're going to go right up here until we get to the up limit switch. Now that note in the lower right hand corner told us we had the landing gear down and locked with the airplane on the ground. And that means that this shows that the up limit switch right now is open, meaning the aircraft is, the switch is not in the down and lock position. But the only time this switch closes and makes a circuit is when the gear is up in lock, because that's what up limit switch means. So notice we do not have a path, and therefore the red light would be extinguished. The red light would not be lit. Remember, the purpose of this particular system is when the gear is in transit, you don't have either light on. In this particular case, we indicated the red light would not be lit. It would be extinguished, as they say in the question. So now let's take a look at what's going to happen to the warning horn under these circumstances. Remember, the circumstances are one or more throttles retarded and the gear in transit. So we have the ground here. Here's the horn. We'll follow it back. And now we have the down limit switch. Now, the down limit switch right now shows the gear down and locked. That's what that note told us over there. In this particular case, then, the down limit switch would be in a different position. Anytime it's down and locked, it's in this position. Otherwise, it'll be over here in this position, away from that. So down limit says the switch is over here when it's down and locked. Otherwise, it'll be over here. There will be a path, and here's the throttle switches. They're closed, and of course, we'll have the nose wheel. It's a nose gear down switch, and it's shown with it down right now. So since it won't be down if the gear is in transit, it'll be up in this position, and there will be a path all the way to the bus for the horn. So in this particular case, if you have the landing gear in transit and you have one or both throttles retarded, what's going to happen in this particular case on figure 19, as we're looking at right here, is that the red light will be extinguished and that horn will blow. Now let's take a look together at figure 19 again, and this time let's you and I do something really, really unusual for an FAA written exam. Let's do something very similar to real life. You can't believe it. Now let's assume that you and I are mechanics. We have a customer come in. He brings his airplane to us. He says, look, I got a problem. He says, I put the gear switch in the up position, but the landing gear won't retract. He says, fix it. And the customer goes away, leaves the airplane with us. Now, you and I don't want to have to examine every single wire in the airplane, so what we do is we get out the schematic, and you and I are going to study the schematic together to see which wires would be involved in retracting the landing gear, and we're only going to look at those wires. So let's do that together. First of all, we'll start off with the electrical source on the left-hand side. That's the bus over here on the left-hand side. We'll go through a circuit breaker, and here is the landing gear switch. Now, we looked at that note earlier, the one in the lower right-hand corner, and it told us that all these switches are positioned as if the airplane's landing gear were down and locked. So we have the switch for the gear selector switch in the down position. Let's move it to the up position. If you move it to the up position, then you'll have a continuous path for the current to go this direction over here till you get to this relay. Now, if this relay were closed, there would be power to the electric motor and the landing gear would come up. But the relay is open right now. Let's talk a little later about how we're going to close that relay. We'll do that in just a few minutes together. But now we'll have the current go through this area all the way down to here, all the way across there, and up here to the up limit switch. Now, this landing gear is shown with the landing gear down and locked, and it would remain in this position. This switch right here would remain in this position until the gear is up and locked, because the up limit switch tells you this switch only changes position when the landing gear is up and locked. So the gear will not be up and locked, so there will be this circuit, this switch will be closed, and the power can go right through here. And now we have the gear safety switch, or otherwise known as the squat switch. Well, the airplane would not be on the ground. It's shown on the ground. We're trying to retract the landing gear, so hopefully we are not on the ground. So this switch will be in this position. The squat switch will not be closed like in this position. It'll be in this position like so. So we'll now have a path for the current to go through here, and the current will go right through here, and that's what's going to close the relay then, goes to ground, and that's what's going to close the relay to make the landing gear motor work until the gear is up and locked, and of course then the relay would be open. So you can see that that is the path that we would need to follow right there, and these are the wires that we need to check. So the FAA is going to ask you on the test, would you need to check wire 12? And the answer is, well, let's see where wire 12 is. Yes, we've put our circuit here in yellow. Wire 12 is in our circuit, so we would need to check wire 12. How about wire number 11? Would we need to check wire number 11? Well, no, wire number 11 is not in that circuit. It's over here, so that wouldn't be involved. How about wire number 15? Would we need to check wire number 15? No, wire number 15 we wouldn't need to check because that's not in the circuit. So through smart work and clever thinking, you and I have found the answer. We'd need to check wire number 12. Now, with your success on studying these circuits, you're beginning to get a reputation, and another customer brings his airplane to you, and he says, look, I put the landing gear down, and I get a green light, and I'm supposed to when I get the landing gear down, but the red light stays on. What's wrong here? Well, once again, you and I consult figure 19. And what we decide we have to do this time is study what circuits are involved in making the red light come on. So let's go to the lower right-hand corner and take a look at that red light down here. Here's the red light, here's the ground, and all we have to have is a path to ground. Now, one thing that could be wrong is the push-to-test feature of this light could have failed, but I can tell you right now that's not the correct answer on the test. So we'll go to ground, let's go through the red light, and let's see what illuminates the red light. Well, that red light will be illuminated whenever you have the up limit switch showing that the gear is up. And we have the gear down. This is showing down, so it should not be illuminated because you should have a broken pathway. So one of the things that you would look for if you were an ace mechanic, as you are in fact, you'd say maybe there's a short in the up limit switch. In fact, that's about the only thing in this entire circuit. So you're going to say, aha, that's what I'm going to suspect, a short in the up limit switch. Now, they'll give you other answers. They'll give you short in the down limit switch. Well, that's not even involved in the circuit. Gear safety switch or nose gear down switch. But this circuit is so simple, the only thing it applies is a possible short in the up limit switch. And believe it or not, you and I have covered everything the FAA asks you about electrical systems on the airframe written exam.